Chapter 14, we're going to be taking a look at a branch of mathematics called graph theory. Okay? There's going to be application, and I'm going to talk about it as we go. But in order to even make sense of application, we need just some basic terminology so that you and I are meaning the same thing when we use the same words. Okay? So this first chapter section, this first section of the chapter is going to have a lot of just terminology to make sure that we have the same meaning. All right? So to start with, we're going to talk about what we mean by a graph. So a graph is a collection of vertices, which means at least one, and edges. Each edge goes from one vertex to another vertex. So when you hear vertex, you can think point. You have edges, you can think the lines that connect the points. So a real basic picture would be something like this. This one would have 5 vertices. And I'm going to draw them connected with edges. So this edge is going to be here. There's going to be one here. There's going to be one that goes all the way across, one that goes down, and one that goes to the side. Now notice, just because they cross does not mean that it creates another vertex. Okay? I drew it like this, but I could have drawn it differently and gotten the same graph. So I'm going to take this same image and I'm going to draw it a little bit differently to show you that I actually have another option in how I drew it where it wouldn't even look like they were crossing, but it's going to defy what you thought that you meant by edges as well. Hang on. Edges do not have straightness. They're just a connection. So one of the images that you might have in mind when we're thinking about this is our campus. Okay? Edges are kind of like sidewalks. Sidewalks do not have to be straight, right? They don't. But in the purposes of what we're doing, the sidewalk or the edge is going to connect one location to a next. So maybe like one building to one building. So one kind of item you can think of is like our campus where the buildings are the vertices, or the vertex items, and the sidewalks are the edges. The thing that doesn't work super well with that argument is that there are some buildings where you can get there by more than one sidewalk, and we can't do that with graphs. Okay, so it kind of falls apart if you think about that. But the edges can only connect to two of them. Simple graphs describe that. So this is a graph in which there's no more than one edge between vertices, and no edge from a vertex to itself. So these are the non-examples. These are the things that do not work. So you cannot have 2 vertices that are connected by 2 edges. This is a no-no. This is not a simple graph. You also cannot have a vertex connected by itself with an edge. There's no circular edges that can go back to the exact same point. Now, you could have, so this is again is a no-no. You could have 2 points, right? And a third point, and you have the ability to, so 3 points, and you have the ability to get back to an edge. So you can go around in a circle. It just has to be connected by points to do it. It has to go through another point to do it. Does that make sense? So this would actually work. We could go back to the same building, if you will, just along a different location, a different edge. When we use the word graph in this chapter, we're going to mean simple graph. So it's going to have that feature. No edges can connect 2 vertices twice, like no two edges between vertices, and no vertice connected to itself. All right, so here is an example of a graph. Take a look. It meets the criteria that we said. I've labeled all the different points that are there. Each point has no edge connecting itself to itself. Each set of 2 points is not connected by more than one edge. Notice what it doesn't have. It doesn't have a feature that says all the points have to have an edge between them. We're going to talk about a very special kind of graph later that has that, but this one doesn't. Okay, and it doesn't have to for it to be a graph or a simple graph. What this question is asking is how many vertices there are and how many edges there are. So we're just counting. So this is the extent, honestly, of the numbers in this chapter. It's counting. Okay, so count for me. How many points or how many vertices do you have? 7. So vertices is 7. And how many edges do you have? It's 7 as well. There's 7 vertices or 7 edges. So if we're counting the edges, each edge is what's connecting one point to the next. So we have an edge AD, we have an edge AB, one that's BE, one that's DE. That's 4 of them. EF makes 5, CF makes 6, and FG makes 7. There's 7 edges. Does that make sense? So you don't count like DG all as one edge. That's not one edge. That's 3 separate pieces. So there's 3 edges there. All right, so using this graph, we're going to do something else here in a moment, but one more definition before we do it. We can talk about the degree of a vertex. The degree of a vertex is just the number of edges that are joined there. Or you could say the number of edges that emanate from there, right, that leave there. So my graph's drawn in again because I want it on the screen, but you don't need to draw it in again. You can just look right above in your notes. We're going to list next to each vertex its degree. So we'll start with vertex A. Let me move this down and give myself a little more space. Vertex A, how many edges are connected to vertex A? 2. How about B?
2.
D?
2.
Okay, E?
3.
That one's 3. Everybody got the 3 there? Okay. F?
3.
C?
1.
Ooh, that one's 1. And G?
1.
1. Okay, does everybody understand what we're counting? Okay, good deal. So the next thing we're going to do is we're going to take, oops, sorry. I think I already did that. Example 2, yeah. We're going to take a look. The next thing we're going to do is we're going to take a look at 2 different kinds of graphs, or 2 graphs that are actually the same graph. So these are called isomorphic. It's a very good math word for you. You sound really smart when you say a word like isomorphic. Okay? Isomorphic just means they're the same. It's great, isn't it? It just means they're the same. So we say that 2 graphs are isomorphic if there's a 1-to-1 matching between the vertices of the 2 graphs, with the property that if there's an edge between the vertices in one graph, there's an edge between the vertices in the other. This is telling you it's the same graph, it just looks different. I already drew isomorphic graphs today. So jot this down and I'll go back and show you the isomorphic graphs that I already drew. So once you finish writing this one down, flip back to the very first definition that I gave you. I drew 2 pictures, right? And I told you they're the same. I just moved where it looked like one of the edges was. Now, these aren't very exciting isomorphic graphs. It's kind of a boring pair, but it is isomorphic. If I were to label my vertices A, B, C, and D, and E like this, I could do the same thing over here, A, B, C, D, and E. And every pair of points that's connected by an edge is still connected by that edge. The pairings are all still there. If they weren't connected by an edge in the first graph, they're still not connected by the edge in the second graph. That's all it means to be isomorphic. It's just a different viewing. Now imagine taking this picture and sort of unpacking it and unfolding it, right? So you've seen these toys before that children have where you can manipulate them and they can like drag them out and then they fold back together, right? This is the image you want to have. I can sort of morph this into something else because it's isomorphic. So let's do one that's a little bit more interesting so you can see that they don't always look alike. Okay? These two graphs do not look alike, right? You might have looked at my first two and thought, well, yeah, I mean, that's sort of obvious. It's no longer obvious if I look at these two graphs. It really is not. But there is a correspondence between these. These are going to be isomorphic. So the directions tell us to determine if they are isomorphic. I'm telling you that they are. So normally you're going to have to make that decision on your own. But the way you decide is by sort of trying to force them to do what you expect them to do. And if they do it, they're isomorphic. And if they don't, then they're not. You see what I'm saying? Right? You're just going to try and make it work. And if it works, then it works. And if it doesn't work, then you say it's not isomorphic. So the way that we start this is we try and take something that seems sort of key. So if you take a look, there are 2 points in the first graph that have degree 3. Do you see them? They're the bottom points, right? This has degree 3 because there's 3 lines coming out of it. And this one has degree 3. There's 3 that's coming out of this. Do you see the 2 points over here that have that same feature? Okay, they have to correspond to one another then. So we're going to do a labeling of points to show that this is going to work or to try to see if it will work anyway, right? This, if it's going to work, have to be the 2 points that correspond to these over here. Does that make sense? Okay, so A is connected to B here in the first graph, and it's connected to B over here as well. I need to label the other points that A is connected to. Well, A is connected to this one up here. So let's give it a name. And we might as well just keep going alphabetical, and we can call it C. And A is also connected to this point over here, and again, we can call it D. So over here, in the second graph, I need to have the other 2 points that A is connected to labeled with the same letters. They're also going to be C and D. And it's a symmetric graph, so it doesn't matter whether you label the top point C or the bottom point C, right? Because the picture is symmetric to itself, right? Top to bottom. So we'll just put C here and D here. So if you take a look over here, every point that A is connected to by an edge, it's connected to by an edge over there. And we have to check that B does the same thing. B, is every point B is connected to in this first graph also connected to it in the second graph? The answer is yes. So if that's the case, then we call it isomorphic. If you're trying to merge this into happening and there's no way to do it, it would not be isomorphic. So the other part of these directions says that we're going to color code corresponding edges. If you have colors with you, feel free to grab them out. Maybe you can share. I meant to grab some in my office and I forgot. I share with those around you if you do. You're going to need, let's see, what do we have here? 4, 5 colors. You're going to need 5 colors. If you don't have colors, then just write them down. It's fine or whatever. You can do it later. So I have an unfair advantage because I have lots of colors on the screen. Sorry about that. All we're going to do is we're going to color code the corresponding edges. So AB in the left-hand graph is going to be colored the same as AB in the right graph. That's a little thicker than I wanted. Let's try it a little bit smaller. So like this, I'm going to color my AB pink here and here. And then I'm going to pick a different color. So we'll go with yellow. I'm going to color AC yellow. It's kind of a pale yellow. And AC, that's pale yellow over here. If you're colorblind, you probably can't see my yellow. Sorry about that. We'll do a little bit darker one. How about green? So let's do CB. So CB is this one right here. So I'll do CB in green. And that's almost the same color as the last one. Let's try something different. How about blue? All right, we'll do CB in blue. And I'll do CB in blue. And then I'm going to change colors again. We'll go purple. I'm going to do AD in purple. That's pretty okay. AD is here in purple. And then I need one more. Let's do a bright green. Maybe that's going to be enough different. DB. Yeah, that's not bad. And DB. This is what it's talking about when it's talking about color coding these. Lots of colors shifting around. So fun. You didn't know you were going to get to color in math class today, did you? No. We are on Thursday as well, so I'll do my best to remember to bring some as well if I can. So, okay, are we all good? Does it make sense what we're doing? This color coding that we just did also verifies that it really worked, right? Every edge that's in the first graph is an equal edge, corresponding to it in the second graph. So these graphs are isomorphic. All right, next one, a connected graph. A connected graph is a graph in which we can move from each vertex of the graph to every other vertex along the edges of the graph. So if you think about our analogy about our buildings and our sidewalks, this means you don't have to walk on the grass to get there. Right? There's actually a sidewalk that will take you there. And then, obviously, a disconnected graph doesn't have that feature. It's a graph in which we cannot move between two vertices along an edge. You legitimately can't get there without jumping off of the edges of the graph, getting off of the sidewalk. Okay, you ready for a picture? Your colors will be helpful for the next one as well. This is the image we're going to draw. So take a minute to draw that if you don't have it already in your paper. The question asks us to determine whether the graph is connected or disconnected, and then to determine how many components the graph has. Components are connected pieces. Okay? It's important to remember what I said earlier about the fact that if you do not see a point on there, there's not a vertex there. Okay, so this location where this sort of looks like it's crossing over right here, almost imagine it like when you're driving and you have highways that go on top of each other. Think of it in a three-dimensional perspective. Those highways do not cross, right? You're just looking at sort of down from the top at a two-dimensional view of it. That's what's happening here in terms of the graph. Has everybody got that idea? Okay, take one of your colors, and we're going to start with the leftmost point on our graph for no particular reason. We just got to start somewhere, and that's where I'm choosing, okay? So I'm going to choose green. That's what's on my screen still. I'm going to start right here. And I'm going to take this point and I'm going to move along to everywhere I can get from that point. So I can move up. From my top point, I can move down. And from this point, I can move back to where I am. And there's nothing else that I can do in that component of my graph. We're going to give this a name. This is what we just created later. But that piece is one component. And now I have to change colors because I'm going to move to a different component of my graph. I'm going to do the one that's inside of here. Okay. That point is connected straight across to this one. And that's it. There's nowhere else I can go. Right? So this is almost like what happens when you have the bridge over the highway. You know, you can just go from one side of the bridge to the other side of the bridge. There's nothing else that can be done. Okay? And then, again, we'll do another point of our graph. And we'll start at kind of a weird place just because I want you to see that it really doesn't matter where you start. You can still work this process out. We'll start right here in the dead center, just for fun. And we want to go along any edge. So we're going to go to the right. All right, here we can go. And then we can go downward. But I had to make a choice when I went to the right. And you might have thought that was a weird choice. It's okay. I could have not gone to the right. I could have just gone down. Or I could have, from that point, gone to the left, and then from the left gone down. So it doesn't matter where you start. You're not trying to sort of do it in any particular order. You're just trying to get anywhere you can from that particular point. So at the point where we are, what we see is that this graph is disconnected. It's disconnected because it took me more than one color to do it. Right? I can't get from anything on the yellow piece to anything on the blue piece or on the green piece. It's not possible. They're not connected. I would have to go off of the graph, like get into the grass, right, in order to do that. So this graph is disconnected. Now, if it were connected, it would have one component, right? It would have one color. Our number of components is defined by how many colors it took us to draw the graph, and it took us 3. So there are 3 components for this graph. Okay, so far so good? Luke?
So you said if it would have all been one color, it would have been connected.
Correct. If it had all been one color, it would have been connected, and there would have been one component. That's exactly right. Did I say something wrong?
No.
You're laughing at me. No? Okay.
No, I was laughing at
You're good. You're laughing at Colton. Okay, that's fair. We can do that. Okay, cool. Anybody good? I mean, everybody good? Not anybody. I want everybody good. Okay, that's better. All right. So we're going to encounter a few theorems along the way. Here's our first one. This is the sum of the degrees theorem. It says that in a graph, the sum of the degrees of the vertices equals twice the sum of the edges. And the first example we're going to do with this is actually not example 5. So jot that down, and then we're going to flip back to a previous picture that we had seen. Okay, the picture that I want us to go back to is the one where we counted the degrees. I redrew it in on mine as number 2. You guys had it as number 1. It was the picture from that already. So I want us to actually at least justify by example that this makes sense. So it talked about summing the degrees, and all my degrees are written on here in yellow, right? So what is the sum of the degrees? Okay, Jasmine says 14. Does everybody agree? Did you get 14? Twice? Okay. Did everybody else get 14? Okay, good. Now what I want us to do is I want us to double the sum of the edges. Okay, so how many edges were there? We counted that previously as well. How many edges were there? 7. And if I double that, what do I get? 14. Now, it should make sense when I do that. The reason this theorem should make sense is because what I'm counting when I count the degrees is how many edges are coming out of this point. But every edge gets counted twice, right? The edge that joins A to D gets counted when I count D, and it gets counted when I count A. So this is a reasonable thing for it to have happen. What this does is it allows us to have a verbal description as well, which is the example 5 we're going to look at, and to determine how many edges we have when we don't actually have a picture drawn. That's how we're going to see it used anyway. So this one tells us to use this theorem and find the number of edges. So we have a graph with 8 vertices. Of our 8 vertices, 2 of them are degree 1, 3 of them are degree 2, 1 of them is degree 3, 1 is degree 5, and 1 is degree 6. So it's like we had that picture that we had before, but it just listed them, right? It lists, we'll just even list it with letters if you wish. A has degree 1, and B has degree 1. And then I have C, D, and E, because it said 3 of them that are all degree 2. I have 1 of degree 3, so we'll call it F. I have 1 of degree 5, G, and 1 of degree 6. Okay? There's no picture, there's just the details. So what is the sum of the degrees? 22 sounds right. Did you guys get 22? Yeah. Where did I get what?
The FG page.
It says 1 of degree 3, 1 of degree 5, and 1 of degree 6. So I just used letters.
Oh, okay, sorry.
So yeah, I just used letters F, G, and H since those are the next letters and wrote down those degrees next to them. Okay, did everybody get a sum of 22? Excuse me. Yeah. Okay, so what does that mean? Well, how many edges are there? That would mean there are 11 edges. There are 11 edges that connect these points together. And if I were asked to do so, I could draw a graph that would have these features. But I couldn't have done that if I didn't know this theorem, right? I wouldn't have known how many edges I would expect in my final graph, and now I do. I know that there's 11. Okay, I mentioned earlier that we're going to have some names for some different ways that we get from one point to the next. That's what's happening next. There's 3 different descriptions of passing through these edges or crossing over these edges. The first one is a walk. A walk is just a sequence of vertices, each linked together by an edge. Right? So I can take a walk from this building to, let's go with the GC. If I walk down the sidewalk that takes me first to the library, and then I take a sidewalk, and again, this doesn't work perfectly because we got lots of sidewalks, but a sidewalk that takes me from the library over to the GC, that would be a walk. I don't have to get on the grass to do it. Okay? Now, not everything's a walk. Legitimately, I cannot take a walk if I'm using sidewalks and get from this building to Bailey, because I have to cross a street, right? That's not a sidewalk, if that's my argument. I have to go off of the sidewalks to do that. So I can't always get from one point to the next. But when I can, that's called a walk. A path is a walk that uses no edge more than once. Okay, so you're not repeating anything. It's sort of the shortest option, right? That's a path. And then a circuit is a path that begins and ends at the same vertex. So if I start, and you guys do this every single day of your lives, you start at your dorm room or your house or your apartment, wherever it is you're living, and you leave there and you go to all these different places, and eventually in the evening time you come back to the same location. That's a circuit. Now notice it doesn't say that the circuit can't cross paths more than once. You Can't go back and forth. None of that's the case. You're just starting and ending at the same place. Okay? So when I left my office from Bailey, if I actually had something connecting it, right? And I came to Stavros and then I went from Stavros back to Bailey, that would be a circuit. Okay? All right. So what we're going to do is we're going to be given a graph. This is our graph. And we're going to be given different itineraries. We'll call them that. There's not a good word. What I want to decide is if this listing of points actually gives me a walk, a circuit, a path. And it can be more than one, and it can be none of them, right? It can fail everything, or it could hit everything. So you have to test every single thing that is listed of those 3 different ones we just did for every different listing of points, okay? So the first one that we have is we have A to B to E. So we're going to sort of trace in our mind, and I'll use colors on my screen. Can I actually do this? Well, I can go from A to B. Definitely can do that. I can go from B to E. I can definitely do that. So if I have the ability to do it with the segments that are on there, right, the edges that are on there, that's called a walk. So this is definitely a walk. That's usually the first one we test, is can it even be done? Now, is it a path? Yes. The only additional consideration for a path is that I didn't repeat any of my edges. And I didn't. So yeah, this is also a path. Is it a circuit? No. Why is it not a circuit? It didn't end at the same point I started at. Now, if I had one additional piece on the end, don't write this in, but if I had it like this, then I would have a circuit, right? And it would hit all 3 of these different descriptions. But we do not. So I'm going to write this in just so that it's in my notes and it's in yours too. This is not a circuit. Because of what you just said, it doesn't start and end at the same point. I'm running out of space. Okay, so what would this look like inside of my math lab? Probably multiple choice, right? Ones where you pick everything that it meets the criterion, or maybe it's a criterion where it tells you, answer choice A says it's a walk and a path, and answer choice B says it's a walk and a circuit, and answer choice C says it's a walk, path, and a circuit, and one of them says it's none of the above, right? It's going to look probably like that. All right, second one. So we're going to ignore the blue. I'm going to change colors. We'll go with yellow. It says I'm going to go from D to C, C to E, E to B, B to D, D to A, and A to E, and E to C, which I don't have a good way to draw that, so I'm going to sort of draw it like this. That indicates that I'm going backwards, but I'm really on the path. I mean, I'm not jumping off. I just need to have a drawing for it. Is it a walk? Yes, because I could draw it, it makes it a walk automatically. Is it a path? No. Why is it not a path? I used an edge more than once. Now, it's probably valuable to notice that there's nothing wrong with the fact that I used a vertice more than once. The problem is that last piece that's sort of drawn off of this, where I couldn't draw it. Everything else was fine until then, right? Yes. Is it a circuit? Why is it not a circuit? I mean, it started and ended at the same point.
Well, it started D, but it ended C.
Oh, we ended at a different point. Sorry. We ended at a different point. That's actually a good reason. There's another reason that it fails. Does anybody know?
It never crosses.
A circuit is a path. Yeah. So if you come back over here, these do hinge on each other, right? The definition of circuit has the word path in it. So it didn't start and end at the same point. That's one failure. But it also isn't a path already. So the fact that it's not a path automatically makes it not a circuit. We didn't even need it to check whether it started and ended at the same place. So it is a walk only for that one. Told you this section was a long section, right? A lot of new stuff. Okay, let's keep going. Complete graph. A complete graph is a graph in which there's exactly one edge going from each vertex to each other vertex. It's complete in the sense that nothing could be added to it to make it more connected. Okay, so this is our next picture. And the question asks if the graph is complete. So complete means I can take a vertice, we'll just take A, and I have an edge that connects A to every other edge. Do I? Careful. Does A connect to B? Yes. Does A connect to C? No, it doesn't. You can get there along a path, right? I can take two edges to get there, but there's no direct way there, right? So this is like flying in an airplane, if you've flown before, and you've got no connecting stops. You don't have a connecting flight. It's a direct flight. There is no direct flight from A to C. I would have to have a connecting flight through B or through D or something else, right? I would have to get there through some other location. So this one is not complete. And all it takes for it to not be complete is for one of those edges to sort of be missing. So there's lots of them that are missing, actually. So we can list one. There is no edge AC. Which doesn't exist. There's a path that gets us there. That's fine. Walk that gets us there. Totally cool. But there's no edge that gets us there. Now, if this image worked, what would it look like? So I'm going to mess up my graph. Let me copy and make it so I can fix it later. I don't know if you guys have noticed my screens, but on my screens I have these little pieces in the bottom. Has anybody noticed them as I've been drawing? It lets me fix my screens later from our work that we've done so that I don't have to redraw them completely. Okay. If I took this graph and I added in a few more edges, I could make it work. So we're going to try that. This is off the cuff trying things. It doesn't always work. I can do A to C, and I can do A to E. I think those are the only ones that we're missing for A. B is missing going to F and to D. C is still missing going to E. I think everything else, no, am I missing one more? D to F, there we go. There's so much going on, I couldn't tell if I was missing anything. I think that's it. A real quick way we could check to make sure that it's it. Maybe it's not super quick, but how many points do I have? Vertices, I have 6 vertices. So if this is complete, every vertice should have degree 6, or degree 5, excuse me. It should go to all the other 5 vertices. So A has 1, 2, 3, 4, 5. B has 1, 2, 3, 4, 5. They do. So this would actually be a picture of a complete graph. It's messy, right? And the more points you have, the messier it gets very quickly. Okay. A subgraph. A subgraph is a graph that contains some of the original vertices and all of the edges that were connected between them before. A coloring is a little different than what we were doing before when we were coloring. A coloring is defined as an assignment of a color to a vertex, not edges, a vertex, in such a way that the vertices joined by an edge have different colors. And a chromatic number is the least amount of colors needed to make a coloring. So in order to talk about a coloring, we need to talk about how we would actually create one, and that's what we're going to do next. So in order to color a graph or to create a coloring for a graph, we choose a vertex with the biggest degree. And they may have several that all have the biggest degree. We just pick one of them, something with the biggest degree. And we use the same color to color as many vertices as we can without coloring two adjacent vertices. We pick a new color and a non-colored vertex of greatest degree, and we repeat. And then we continue this process until all vertices are colored. There is a direct application of this that you're completely probably unaware of. But this process is how map makers color maps. Think about the map of the United States. You do not need 50 colors to color all the states so that no two states that are set next to each other are identical colors. So how many do you need? This is actually how somebody would decide how many colors they would need to color a map of the United States. And it's not just the United States. You could use countries in Africa or something like that. Same idea. Coloring them all different so that they don't connect to adjacent countries with the same color. Okay, you ready to try one? Writing it down is harder than doing it. That happens a lot with descriptions of things in mathematics. So, I don't know why the picture's not here. The picture is the same one that we had done before, but it actually has a point in the middle. So this is actually the picture we're supposed to have here. It looks like this. Hang on. No. That's not going to work. All right, let me just draw it in like this. It's not quite as fuzzy as the other ones, but that's point G. Okay, this is the picture you're supposed to have. Is this drawn in your notes? Yours drawn in yours, just not drawn on mine. Okay, no problem. Okay, so this is our image, and we need to figure out a point with highest degree. So, looking at all of these points that are listed here, how many of them there are? How many of them are there? There's 7 points listed. Which one has the highest degree? G. So we're going to color G something. I chose yellow. And I can't use yellow anywhere else. Why? It's not just because I already used it. That's part of it, but there's a reason I can't use yellow again. Every point that's connected to G cannot be colored the same color as G. And what do you notice about the points connected to G? It's connected to all of them, right? G is connected to every single other point. If there were some other point that G wasn't connected to, I could use the yellow again. That'd be no problem. But G's connected to everything, so I can't use yellow again. So I need to switch colors. We'll go orange. Okay, so I need to pick another point of highest degree. What would you like to pick? A. And it doesn't matter, right, Justin? Because they all match now, yeah? Okay, so we're going to draw A in as orange. Now, clearly A and G are different colors, and also I can't make A and B the same color, and I can't make A and F the same color. But there are other vertices that I can color in orange. Tell me another vertex I could color in orange. C or D or E. I have 3 options. And I want to color as many of them as possible, but I actually can't color all 3 of them. Why? Because they will be connected. So the one that I don't want to color is I don't want to color D. And the reason I don't want to color D, orange that is because then I can't color anything else in orange. If I choose to color C in orange, then I can also color E in orange. So I get more bang for my buck, right? I get to use the orange more times. And then I need to switch colors.
Question.
Yes.
Why can't you make B orange?
I can't make B orange because it's connected by an edge to A. Yeah. Please keep asking because it takes a while to all the we're trying to connect dots, literally and in our heads, right? So please ask. Does everybody understand why I can make some coins orange and not all of them? Okay, good. So now I need a different color, and I need to pick different points. We'll just go alphabetical order, and we'll go to B next, and I'm going to use green. What else can be colored in green? F and D. All right. Now, could I use more colors to color this graph? Yes, but the goal is as few colors as possible. And you might be thinking, well, like, why do you care? I mean, like, why would the map maker care how many colors that they colored the map in? And there's actually a really good reason for that. And it has connection to us in ways that's very old school. So the way things used to be printed, like printing press stuff, is that if you wanted to print something in red, you had to run it through the printer and it only printed red. And then if you wanted to print it in orange, you had to run it through and it only printed in orange. And blue, and it only printed in blue, whatever. And so you wanted to run it through as few times as possible because it costs less money, right? This is not my color printer of today, right? It's just not. But that was the goal, was to actually cost savings on the maps. So how many colors did I use? 3. So since I used 3 colors, this has a chromatic number of 3. I'll write that down. The chromatic number is 3. Okay, we have one more problem in this section, and it's going to be the most interesting graph you've seen today. Are you ready for it? Yeah, absolutely. And we're going to draw it together. It's not drawn on your paper. So this is the application of graph, of things that you might not have thought graphically. Like I give you pictures of the sidewalks, and you can kind of image that in terms of the pictures we've been drawing, and this one's not like that. So we're going to go to a party, okay? There are 4 males that go to the party and 5 females. If it were at OBU, it'd probably be like 4 males and like 8 females, right? Yeah, okay. During the party, each male is going to dance with each female once, or well, dance with each female. And no female or male pair is going to dance together. That's the constraints of the problem. We're going to draw a graph with vertices representing the people. So the people are the points, okay? And the edges are going to represent the dance that they had. Got it? The points and the edges represent not sidewalks and buildings, people and dancing. All right? And the question is, how many edges are there in the graph? So I need another screen because there's no way I'm drawing it on that screen. So the easiest way to do this is to do the vertices in sort of 2 columns. One column over here is going to represent the vertices that are the males, and then the other column is going to represent the vertices that are the females. Everybody with me? Okay, so we need 4 dots, right, for the males. So I have 1, hang on, I want to make it a little bit bigger than that. 1, 2, 3, and 4. So these are my males on the left. And then I'm going to put the 5 females on the right. Okay, so the first dot, male number 1, is going to dance with every single young lady over on the right. And this line represents the dance. All good so far? That's male number 1. Male number 2 is going to do the same thing. He's going to dance with each of the 5 females on the right. That was not very good. Let's try that again. That's better. No, it's not. That is. All right, male number 3, same thing. And male number 4. Okay, definitely the most interesting graph of the day, right? For sure. Got the most going on at the very least. The question asked, however, how many edges are there in the graph? In other words, how many dances, individual pairing dances, took place? There's 20. Now, there's more than one way to do this. It's kind of difficult to actually count the edges because they overlap so drastically. How could you do this if you didn't actually count the edges? You could multiply. So tell me what you multiplied. Yeah. So there's 4 men, and each of the 4 men had 5 dances, right? So there's 20 dances, and dances are representing my edges. You could also think about this from the degrees theorem that we'd had. If you counted each of these vertices and found their degrees, you'd have 5, 5, 5, 5 on the left, and you'd have 4, 4, 4, 4, 4 on the right. That would be a sum of 40. So the edges would be half that, and it would be 20. So there's different ways to get to the fact that we have 20 edges, but we will get there with 20 in any of those ways.